All right, hopefully you remember a few lessons ago we talked about perimeter and area and how with similar figures the perimeter maintains that same similarity ratio, but when it comes to the areas we have to square that similarity ratio in order to see how the areas compare amongst similar figures. Well, here we're looking at a few problems that relate some of these same ideas here. It says a rectangle is half as tall as it is long. A rectangle half as tall as it is long. If its height is reduced by half its original height, what is the ratio of the new rectangle's perimeter to the original rectangle's perimeter? Okay, well, if its height is reduced by half, so now that means this would be a fourth of the original length, and this side would have to be half its original length. See that? Its height is reduced by half, so now that's a fourth, and that's always going to be half the length there, so this is the new one here. What is the ratio of the new rectangle's perimeter to the original rectangle's perimeter? Well, this right here, we can see this would be a fourth the length, this would be half the length, and so the perimeter here would be 1.5 that original length. And we want to compare this to the original rectangle's perimeter. So that would be half, that's 3L. And so when we simplify this, the L's cancel out and we get a half. It is a half. And notice how it went down by half. We shrunk the height by a half, and so that scale factor maintained all the way to the perimeter. Here it says, find the area of each polygon, describe how each change affects the area. Triangle ABC has a base that is congruent to its height. If the base is dilated by a factor of 2, what is the ratio of the new triangle's area to the original triangle's area? Well, triangle ABC has a base that is congruent to its height. The base is congruent to the height, so the area of this original figure here, this would be 1/2 base times height, so this area would be 1/2 b squared. Look at that. Well, the new triangle's been dilated by a factor of 2, so now the height is 2b, the base is 2b, so this would be 1/2 base times height, 1/2 base 1 times base 2, which gives us 2b squared. Whew. All right, so when we find the ratio of the new triangle's area to the original triangle's area, that's 2b squared over 1/2 b squared. B squareds cancel out. 2 divided by 1/2 gives us 4, or 4:1. Notice it increased by a scale factor of 2. That's 2:1, and if we square the 2 and we square the 1, we get 4:1. So that makes sense. We're seeing how these are playing out with just like we expected. In the second one, a parallelogram's base is twice as long as its height. I'm going to clear this out so we have some space. A parallelogram's base is twice as long as its height. So the base is twice the height. If the length of the base is doubled and the height is halved, what is the ratio of the new parallelogram's area to the original parallelogram's area? So the length of the base is doubled. So just imagine that's doubled. This is now 4 times that original height, and the height is halved, which means This is half the original height. What is the ratio of the new parallelogram's area to the original parallelogram's area? Well, this would have a area of 2h squared. This would have an area of 2h squared. When we compare one to the other, it is 1 to 1. All right, it says the circle's radius is increased by a factor of 3. Find the ratio of the circle's new area and circumference to the original circumference and area. Well, whatever our original radius is, we know the circumference would be 2 pi r. We know the area would be pi r squared. But if we increase it by a factor of 3, well, the new circumference is going to be 2 pi times 3r, which is 6 pi r. If we plug it in for the radius and the area, this would be pi times 3r squared, which gives us 9 pi r squared. We want to find the ratio of the circle's new to the original, and so if we do that for our circumference, that's 6 pi r over 2 pi r, which gives us 3 to 1. And down here, if we compare the new to the original, this gives us 9 to 1. So again, what we expect with the perimeter, it's going to maintain the same similarity ratio as our scale factor gives us, but for the area, we had to square it. Square the 3 to get 9, square the 1, we get 1. Finally, Bev. Oh, Bev is having a pool installed in her backyard. Her backyard is a rectangle with a length that is twice as long as its width. It's got a length twice as long as the width. Bev decides the pool will also be a rectangle, but will only run 3/4 the length of the backyard and will be half as wide. What is the ratio of the pool's area to the backyard's area? Well, this will run 3/4 the length. So what was 2w is now going to be 3/4 times 2, 3/4 of that 2w, and it is going to be half as wide. Okay, 3/4 times 2w, this does give us 3 over 2w, so it's just a little bit easier to work with. We want to know the ratio of the pool's area to the backyard's area, so we're going pool to backyard. Well, the area of the pool, 1/2 times 3 over 2w, which gives us 3/4 w squared, and we're comparing that to our backyard, which is 2w squared. So if we compare that as a fraction, 3/4 w squared over 2w squared, we get 3/8. It is 3 is to 8.